Hello everybody, my name is Amit and I'm going to talk about our paper Shape Correspondence by Aligning Scale Invariant LBO Eigenfunctions. This is a joint work with Halimi and Professor Kimmel. So our motivation in this process was to create a robust and intrinsic descriptor in an unsupervised optimization process without any need of labeling, which will also be explicable in a way which we can justify every step we take. Before I dive into our method, I want to talk a bit on the Laplace-Beltrami operator, LBO in short. You can see the definition of it here, where G is the metric tensor, and it is basically a generalization of the Laplacian from the Euclidean domain to a manifold. Since it only depends on the shape metric and not on its embedding, it's an intrinsic operator, and thus its eigenfunctions are intrinsic and potentially used as intrinsic descriptors. Another version of the LBO that we use in our work is scale invariant LBO, which define the same but with a different metric that you can see here, where K is the Gaussian curvature. This metric causes the operator to become invariant to scaling, and to emphasize this point, this image shows two figures, where the figure in the lower line has a scaled down head and the scaled up end. These figures are colored by the scale invariant eigenfunctions, and as you can see, the scaling did not affect the value of these eigenfunctions. The scale invariant LBO eigenfunction also candidate to be used as descriptors. They are intrinsic, and they are obviously a scale invariant. However, there are two main issues that prevent us to use them as descriptors, and not only them, but also in any other version of the LBO, its eigenfunction faces these issues. The first issue is the sign ambiguity, where if a function is an eigenfunction for an operator, then the negative of the function is also an eigenfunction for the same operator, which leads us to a problem like this, where here we can see the same human in two different poses, meaning the two figures are nearly isometric, and we color each figure with its second eigenfunction value, where blue represents negative number and red represents positive number. We can see that one is the negative of the other. This issue is especially undesired for descriptors because instead of being just inaccurate, the descriptor points in the other direction. The second problem is the rotation in the spectral domain, which can happen in the case where two shapes are only nearly isometric. And here is an example for it, where the second and the third eigenfunction of one pose are the linear combination of the second and the third eigenfunctions of the other pose. In a broader look, if we take the first pose eigenfunctions and try to find the rotation that gives us the second pose eigenfunctions, the result is the blue frame matrix that you see here, which is a band unitary matrix. And this matrix we aim to find. And why do we aim to find it? Well, basically because with it we can align both shapes' eigenfunctions and create a robust and intrinsic descriptors. To find it, first of all, we use our knowledge on its structure, and we impose a band structure by an Hadamard product of a mask with a learnable weight matrix, which results in the matrix R that you see here. This is the matrix that we optimize in our framework. This is our framework. In it we use both the LBO eigenfunction and the scale invariant LBO eigenfunctions. The LBO eigenfunctions are used as a basis function for the functional map framework, where the scale invariant eigenfunctions are used as descriptors. We multiply the first pose scale invariant eigenfunction by R and the other pose eigenfunction by R transpose. So basically, we don't look for the rotation between them, as I said before, but only for the half of the rotation. Then we input the product to the functional map framework and the output the functional map C. We use C to create the soft corresponding matrix P, and we use this soft corresponding as an input to our free losses, on which I will talk next. From those losses, we backpropagate the gradient to the matrix R. The first loss that I will discuss here is an over loss that we use in our framework. It basically bootstraps our optimization process, and it relies on the fact that a good alignment will give us a good correspondence, and if so, then we can use this good correspondence to check if it was really a good alignment. To do it, we multiply the first pose scale invariant from the left by the induced correspondence that is defined below, and from the right by the rotation matrix R. In the case where the correspondence and the rotation are perfect, the product should give us exactly the other pose scale invariant eigenfunction multiplied by R transpose. The second loss that we use is the unsupervised loss by Halimi et al. This loss relies on the fact that the geodesic distances between vertices are preserved between isometric shapes. This loss penalizes on the changes of distances between vertices given a correspondence. It is a good match for our framework because we try to correspond between two nearly isometric shapes. However, since they are only nearly isometric shapes, then the ground truth does not zero on this loss. Unfortunately, in our optimization process, we reach a lower error on this loss than the ground truth, which lead us to an error in the correspondence. To deal with this issue, we added the cyclic loss by Ginzburg and Raviv. This loss used two soft correspondence matrices, one from the first shape to the second, and the other from the second shape to the first shape. This loss transformed a distance map to the other shape with the first soft corresponding matrix, and the second soft corresponding matrix transformed it back to the original shape, and it penalized on the difference. This loss gets 0 in the case of the ground truth, and when we use both losses, the correspondence error is improved. Now I will present some of our results. Here you can see the alignment result given by the relative error between eigenfunctions versus the eigenfunction index. The purple line represents the eigenfunction before the optimization. The orange line represents the eigenfunctions of our method only with the unsupervised loss. The yellow line represents the eigenfunction of our method with the cyclic loss and the unsupervised loss, and the blue line represents an ablation that we did to check our optimization process. In it, we used the same distance matrix for both shapes, which is not a feasible scenario, but we wanted to check whether the optimization process can improve without the ground truth error. And as you can see, it did, and this experiment led us to add the cyclic loss to optimization process. Here is a qualitative result for the alignment. The upper image represents the eigenfunctions before the process, and the lower image represents the eigenfunction after the optimization. Each 4 columns represent different indices of the eigenfunctions. The first 4 represent indices 2 to 5, the second 4 represent indices 12 to 15, and the last 4 represent indices 22 to 25. As you can see, the optimization process aligned these eigenfunctions. Here is a quantitative result for the correspondence of Faust's dataset. And as you can see, our method, with both losses, the unsupervised loss and the cyclic loss, got better correspondence than the unsupervised loss FMNet by Halimi et al., which was the state-of-the-art method in the self-supervised challenge. Another thing I want to point out is the correspondence in the case of our ablation, which shows that without the ground truth error, our optimization can reach a much higher correspondence. Thank you for listening.